Imagine how society was hundreds of years ago. You kind of just woke up and whatever happened that day was what happened. Sometimes you would have a severe weather outbreak with thunderstorms, hail, tornadoes, and because it would happen suddenly, people couldn't prepare for it. So the advent of numerical weather prediction and climate models is probably one of the most important breakthroughs we've had as a society, being able to predict weather, because it has been a major lifesaver.
That is an excerpt from an interview with 2025 MacArthur Fellow Ángel F. Corraliza, an atmospheric scientist investigating the mechanisms underlying tropical weather patterns. He combines deep knowledge of the physics of atmospheric waves with keen analysis of observational data and climate model simulations to shed light on atmospheric dynamics that influence global weather patterns and phenomena such as tropical cyclones and monsoons. In this episode, we go in depth with Ángel to learn more about him, his work, and his exceptional creativity. Let's hear more from his interview.
My story as an atmospheric scientist began when I was a kid. I like running outside. I like enjoying the outdoors. I'm from Puerto Rico, so it's tropical climate. It's hot and humid pretty much every day of the year. And I was very curious because I would just see the daily progression of blue, sunny day, turning cloudier until like started raining. And that happened like clockwork almost every day in my hometown of San Sebastián. And then we had a hurricane, Hurricane George. We can't evacuate in Puerto Rico, so we had to weather the storm. And so it had really strong winds, and we had to feel and experience how the hurricane was like. And it was kind of scary, but it was scary in the kind of way that it strikes you. Like, how is something like this possible? Why can weather be so violent? And after that, I was hooked. I really wanted to understand. I really wanted to know what drove weather in the tropics, and that was what led me to here. The tropics were kind of elusive for scientists. There was a bit of a paradigm shift about 30 years ago in which people started to think of the tropical weather systems somewhat differently. Before then, people thought that the tropics could be explained by the same ideas that people used to explain the middle latitudes. That turned out to not quite work. In the mid latitudes, you get these storm systems that are constantly moving and temperature varies wildly. You can have a day that's actually really warm and then a couple hours later, it gets really cold. But in the tropics, you do not see that. You see a completely different arrangement of weather systems. It's almost like we live in two different worlds, even though we're on the same planet. In the tropics, you get hurricanes, you get thunderstorms, you get monsoons, you get El Nino, you get all these other patterns that you do not see in the mid-latitudes. The tropics are a pretty unique place, right? They receive more sunshine than the middle latitudes. They're actually pretty warm almost the entirety of the year. You see this high temperature that is associated with a variety of weather patterns. And these weather patterns are usually associated with fluctuations in water vapor, so humidity. So you get these blotches of high humidity and these blotches of really low humidity, dry air. And in association with these movements of humidity, you actually see cloud patterns that are actually focused in the areas where the humidity is high, and you get mostly clear skies in the areas where the humidity is pretty low. And so we're trying to understand this freeway interaction between the wind patterns that move humidity around, the humidity itself, and then the clouds that are moving around with this humidity. When I went to graduate school, I went to the University of Washington. I was put on this project to study the Madden-Julian oscillation, or the MJO. The Madden-Julian oscillation is this enormous wind, rain, cloud, and moisture pattern that you see in the tropics. It is one of the biggest weather patterns in terms of scale. Russia would fit inside of the MJO. While it moves, it actually creates a lot of rainfall. It produces hurricanes. It is massive. And it has major implications, not for the tropics only, but also for the middle latitudes. And no theory up to that point really explained it in a satisfactory manner. So what I did was that I took my training and observations that I had prior to then, and I said, what if we take observations and use this to inform theory? So we decided to then developed a linear model, a basic wave model where we just wanted to answer and think about the MJ in a really simplified setting. The most important thing for the Madden-Julian oscillation is that it is this giant oscillation of water vapor humidity. And when the humidity goes up, it goes up at the scale of thousands of kilometers. And with that, rain just picks up. It starts raining a ton, and then wind patterns develop in association with that, and then the wind patterns actually cause all that rain to start moving eastward about 5 meters per second. When I developed that model, there wasn't really a theory that fit the observations that well. And then after that, I was like, this is what I want to do. I want to use theory to understand weather patterns in the tropics. And the insights that I get into the MJO, we just expanded it to all these other tropical weather systems. What is most unique about my work is that there aren't really that many tropical meteorologists, people that are experts in weather and climate of the tropics, that actually combine the theory. So when I say theory, I'm talking about the math, the physics, the equations, with the observations and the modeling. You can actually get a really basic understanding of many of the important weather and climate features with really simplified models. Weather models are these enormous pieces of code, computational code. They're written into these computers and they're run on these enormously powerful supercomputers. So that's what we call a numerical model. There are also theoretical models. These are the simplifications of these numerical models. I want to be able to catch the essence of weather patterns, of climate patterns, and inform people like what are the most important features that drive these patterns. Nowadays, we take the fundamental laws of physics and the equations of motions, and we've taken them to the next step. We can actually plug these into computers, give all the knowledge that we have, all the observations that we have, and give us an outlook of how decades from now might look like. We know because of theory and because of these models that there are some things that are going to happen, for sure. One of them is that it's going to be warmer, the ice caps are going to melt, it's going to get way, way more humid. And there's a couple consequences of that. One of them is that, for example, rainfall events could actually lead to heavier rain, more floods, more flash floods. Hurricanes could potentially be stronger. Also, heat waves are going to get more oppressive, and that's going to be a major consequence that we're really concerned about in the tropics. I want people to really appreciate our planet. Earth is beautiful, it's magnificent, and Earth is incredibly complex. It is not this simple piece of rock with water and air. It is actually, dare I say it, more than the sum of its parts. It is interactions between the ocean, the atmosphere, between plants and the atmosphere, between the atmosphere and cities. Everything's interacting. Ice, people, air, ocean, animals, everything is an integral part of our planet. And they interact in like extremely complicated ways. But even though there's so much complexity, there's still simplicity. And so I want people to get up every day and be amazed and be like, wow, this planet is cool.
Ángel F. Corraliza is an associate professor in the Department of Atmospheric and Oceanic Sciences at the University of Wisconsin-Madison. His research has been published in Current Climate Change Reports, Journal of Atmospheric Science, and Nature Climate Change, among other leading journals. The MacArthur Fellows Program identifies and supports extraordinarily creative individuals with a track record of excellence who demonstrate the ability to impact society in significant and beneficial ways through their pioneering work. To learn more, visit us at macfound.org.